Today we're going to talk about Karnaugh Maps, which are by far the most powerful tool in all of digital logic design. I think that if you spoke to any upper class ECE student or to any professional electrical or computer engineer, digital logic designer, they would definitely agree that Karnaugh Maps are an incredibly powerful tool. Karnaugh Maps are going to eliminate the need to do an awful lot of Boolean algebra, which if you've just completed the assignments for the previous lesson, will probably be good news for you, because it means that we'll be replacing a tool that is challenging and at times frustrating with a tool that is almost fun, that we're going to be able to use sort of problem solving techniques and to be able to attack problems in interesting and novel sorts of ways. Now, one thing that I wanted to sort of let you know, although you haven't seen enough examples of this to be sure of, remember that last time we saw that we would have a truth table, and I've expanded this out to a truth table of 4 variables with 16 rows. And if it happens that the rows tend to be adjacent to each other, that's usually a good indicator that the equation is going to simplify down. So you can see here I start off with the full version from 4 different rows. I reduce, and eventually I get down to not A and B. But that isn't always going to be the case. Sometimes there'll be adjacent rows that really don't combine well. Sometimes there'll be non-adjacent rows that do combine well. So here you can see an example where I have 0001, 0001, 0001, 0001. That combines exceptionally well. What we're really looking for here is not that they are physically adjacent to each other, but that they are logically adjacent to each other, that we can combine 2 cells, there are 2 rows that contain very similar pattern of A, B, C, and D. What we need is a tool to be able to visually recognize when those cells are adjacent to each other. When for example, to identify, for example, that this one right here is actually almost the exact same as this one right here, that they really only differ in one of the 4 variables. We need a tool to be able to recognize that and to group those together into a simpler function. Happily, Karnaugh Maps are that tool. Now, what I've got here is 3 pictures of Karnaugh Maps. The figure A is for a 2-variable Karnaugh Map. Let's start with that one. You can see here a 2-variable truth table will have 4 rows in it, 2 to the 2nd power, and there are 4 cells. So every one of these cells will correspond to a row of the truth table. Notice that there are 2 variables, A and B, and that A goes across the top row. So this column corresponds to A equals 0, and this column corresponds to A equals 1. Similarly, B goes down the left-hand side, so the top row corresponds to B equals 0, and the second row corresponds to B equals 1. So if you point to any cell, I can tell you what is the value of A and what is the value of B for that cell. If we expand to 3 variables, then we're going to put both A and B across the top. And the order A, B is the same as the order of the numbers that are shown here. So I have A equals 0, B equals 0, A equals 0, B equals 1, A equals 1, B equals 1, A equals 1, B equals 0. And then down the left-hand side will be C equals 0 for the first row. So this entire row has C equals 0, and this row has C equals 1. Now, one thing to notice here is that the 3rd and 4th rows are swapped from what we would expect from binary ordering. So if we were just using binary numbers, binary counting, we would say 00, 01, 10, 11. But these 2 rows are swapped because Karnaugh Maps use what's called gray code. And gray code is a code that ensures that adjacent numbers only differ by 1 value, only differ by 1 of the bits. So if you look here, 00 to 01 only differs by B, the second number. 01 to 11 only differs by A, the first number. 11 to 10 only differs by the second number. And then we can actually wrap around, and we see that 10 wraps around to 00 only differs by A, the first number. So this is the reason why we go out of order. We're not out of order. We're in gray code order. We're just not in normal binary order. But it's something that you're going to accidentally trip up every once in a while, so you got to be extra careful about that. Now notice that I put these little numbers in the top corner of each cell. That number corresponds to the binary equivalent of A, B, and C for that particular cell. So here you can see A equals 0, B equals 0, C equals 0. Well, that's the binary equivalent of 000, which is just 0. 001 would correspond to 1. 010 corresponds to 2. 011 corresponds to 3, and so forth. So if we go in the right order, we go 0, 1, 2, 3, skip a column, 4, 5, come back, 6, 7. And that's actually what I say in my head as I'm filling in the K-map. 0, 1, 2, 3, skip to 4, 5, back to 6, 7. And you'll become accustomed to this. You need to learn how to draw these blank K-maps without having to give them any thought. And then we'll fill the K-maps in and we'll use the K-maps, but you should become so comfortable and so familiar with drawing these that it is second nature for you. Part C here, you can see this is a 4-variable K-map. A and B are across the top, C and D are down the left-hand side. And so I have combinations of 2 variables, A and B both being 0, that's this column. A and B being 0 and 1, that's this column. C and D both being 1, that's this column. And I've once again filled in the 0, 1, 2, 3, 4, 5, skip to 6, back to 7, skip an entire column, 8, 9, down to 10, back to 11, 12, 13, down to 14, back to 15. So that's the order in which we're going to need to fill the K-map. So the first step is to understand that what we're looking for is logically adjacent ones, and we'd like to group those ones together into larger groupings that are going to be simpler to represent, and we need to be able to do that using gray code, and Karnaugh Maps are designed to use gray code. Okay, so the third and fourth rows and columns are swapped with each other, and we use gray code to ensure that only one input value changes between adjacent columns or rows. The next thing we're going to see in the next video is how to fill the map, and then once we've filled the map, we'll learn how to group the map, and once we've learned how to group the map, then we'll learn how to write the correct equations for our groupings, and that's it. We only have 3 things that we need to do. We understand the basics of Karnaugh Maps. Now we're going to move on to filling the map.